I got 10 extra for that too. And I'll wash my hair. Yep.
The table.
Demonstration?
Yeah, at least a small one. Hmm?
It's a very interesting chapter.
No. You like it?
Yeah, I like this one.
Yeah, the homework in the lab. All right, let's go ahead and get started. So just a quick announcement. We have our clubs fair on Wednesday. Uh-oh. Sorry, my Wacom mapping is off. There we go. Okay, sorry about that. So clubs fair on Wednesday for the Riverside campus. So it's today on the Redwood, but I don't think anybody will be there. So it's from 12 to 2 p.m. And Alero, you just walked in. I'll put you on the spot. Will there be food? Or is there going to be pizza on this one? Do you know?
We didn't allocate for pizza. There'll be a bunch of stickers for sure. Folks will be bringing stickers as well. I'm gonna have to go through your attendance, but I know for sure most times we'll be swing up the stakes.
I know, I'm sorry. You walk in, we're like, clubs. But so come for those stickers, come check out the clubs, and of course you can join Earth Club if you want to, I don't know, do hiking and outreach, since now I've turned it into outreach. Any other announcements or anything? I know I'm behind on grading y'all's stuff, so don't fret. I need to sit down and grade. Any other questions or announcements or anything? All right, so let's look at chapter 15, and let's put it in context of kind of where we are. So, right, last chapter we talked about gases, and we said, well, kinetic molecular theory, there's no interaction. And so now, right, we're going to study, well, what are those interactions? So now we're actually studying those interactions looking at those intermolecular forces and then kind of seeing how those intermolecular forces translate to the properties we see, like why is helium a gas? Why do we see water, you know, as a solid, a liquid, a gas? All these things. And so the theme is, of course, structure determines property. And so we'll look at our structure and kind of be able to look at our molecular structure. We'll talk about polarity again, so putting in some concepts together. And so again, how that determines the strength of the intermolecular forces. And so really important that we establish this early on. So just pay attention to the word here, right? Inter. And so you want to think about interstate highway. And that means between molecules, right? Like between the states. And a lot of people just mess up this language, and you don't want to confuse it with our intramolecular forces. And maybe we'll put that, so intramolecular forces. Those are the covalent bond, the ionic bond, all that. So we're not talking about this, right? We're not breaking up our molecules, right? When we talk about water boiling, we're never disrupting our bonds. So we're never breaking, right, our oxygen-hydrogen bond, but we're talking about rather these interactions between the molecules. So we'll be looking at this sort of interaction. And so this is a hydrogen bond, but I don't want to jump too much. And so again, intermolecular forces are attractive forces between all our molecules and atoms. And so again, we'll see how those intermolecular forces dictate whether things are liquids or solids or gases. And so again, they're responsible for why things are at the phase they are, at the temperature they are. So again, why are things a gas? Why are things a solid? All of that depends on the intermolecular forces. And then, of course, we'll look into how energy plays into that and the energy involved in changing and doing those state changes, because that's really important as well. And so, of course, we'll look into this more, and as we add thermal energy, right, then we learned, especially in our gas chapter, our molecules tend to move more, and so, again, more energy. In general, they tend to be gaseous. And then thermal energy is low. We saw that matter tends to be a liquid or a solid. Again, like even liquid nitrogen condensing, liquid oxygen, all those things at extreme temperatures can still become liquids or potentially even solids. And so, of course, we'll be looking at the relative strengths. And so we can start to think about this. Well, if something's in a gas state, and right, we mentioned these properties, so it had an indefinite shape and indefinite volume. Those are just our basic properties of matter. And so that's going to be related to weak intermolecular forces, and again, we'll go through and kind of analyze this more, but that gives us a good hint. And then liquids, especially again, just at our like room temperature. And so we can start to think about what liquids this might be. So anything from water to, you know, you probably have some experience with ethanol potentially or isopropanol. So just think of what organics do you work with. Even, you know, gasoline. I don't know if people do any like paint stripping or what you can even get. Can you still buy MTBE, for example, here? Methyl butyl ether. Throwing out things people might work with. And so we'll see, right, again, look at how their shape and volume properties are related. So we know this, so we mentioned liquids have an indefinite shape, and so, right, they can still kind of move past one another. And so there's still some sort of intermolecular attraction, right, keeping them together, keeping them in that liquid phase. And so we can kind of think about that as moderate interactions. And then so solids, especially when we look at like our crystalline network solids or metals, obviously, right, definite shape, definite volume, and then relatively high density, of course, and then strong intermolecular forces. And right, a lot of these also have pretty high melting points. And right, we can think about metals and salt crystals. So let's see. So this is just our comparison of densities. So we're looking at water. And so again, as we go from gas to liquid to solid, for the most part, they become more dense. And then water, of course, is a little bit anomalous, where it has a lighter density as a solid due to how it packs. So you can see it's 0.917. And so like it mentions here, right, that's not normal. So most solids have a greater density than their liquid. So water is unusual. Yeah, I mean, that goes into like a whole tangent of like your icebergs float, and then exactly you can have life on the bottom. So it's,
Well, every winter, if that was the case, all the ice would float down to the bottom and just build up, and then all the fish and everything in there would be dead.
that's true too. That's yeah.
Also why things explode when you freeze them.
Also true. So yeah, don't explode your drinks in there. And so, of course, liquids, this is, again, just kind of a review of our general properties. So again, we mentioned that they have their defined volume, so they're still closely packed, but have that ability to move around. And so we still say liquids are incompressible, but again, they can obviously take any shape. And so again, they don't have enough freedom of movement. So basically, right, they don't have enough energy that allows them to escape. And so again, right, we're seeing that liquids have higher densities than gases and are incompressible because our particles are closer. And so blah, blah, blah. And then again, right, gases, we just talked about gases. And so we mentioned freedom of motion. They're constantly moving. So, right, think back to our root mean square path, right? They're either always moving in a straight line until they collide. And again, they're just going around in a random pattern and free flowing. So again, gases expand to fill and take the shape of our container. And so again, the molar volume of a substance in the gaseous state is much greater than the molar volume of a liquid or solid state. And again, you can put water in context to kind of help you with that. And again, just roughly, we set it STP. Anything is going to be 22.4 liters for a gas. But then trying to translate that, so water as a liquid would be about 18 grams per mole. And of course, density of 1, so big difference, right? Just thinking about the different phases, so using water. And so like we've seen and talked about, so again, gases are compressible, and again, we can compress them all the way down even to a liquid form. And so we'll also talk about solids and how they pack. And so we'll revisit this with our kind of crystal structures later in the chapter. And so, right, just in general, solids, of course, pack together, and then they get in a fixed position. But we'll look at, and so this is what a lot of what I wanted to do as an inorganic chemist. And if you want to get a crystal structure of something, to get a pretty picture of your molecule, you have to slowly crystallize out your compound because you want it to grow orderly, basically, as a crystalline solid. So a crystalline solid has some sort of defined crystal packing structure that basically is a unit that repeats And that's what makes it look nice and shiny and pretty, right, then to our eye. And again, we'll talk about this in at least a few of the ways they can pack later on in this chapter. And so examples you would be familiar with are salt, of course, again, right, think about how it crystallizes out. And you can grow pretty nice salt crystals if you get really bored at home, right? Just take your salt, boil it up, dissolve it, cool it back down, right, after you made your supersaturated solution, and then you should have really nice fat salt crystals. So that's always kind of fun to do, especially with younger kids or something. And of course, diamonds would also be a nice crystalline solid structure. And again, you can tell from its shininess how well it packs. And then you could get into more of the science of the diamonds, right? That goes into like the clarity and all that, so just how well it packs and how nicely that crystalline structure is ordered. So obviously, right, those big diamonds are desirable that have that huge carat size, right, and then good clarity, and that's just all dependent on how that crystal just grows and grows and grows over time. So that's why it's so desirable. Of course, now they make synthetic diamonds, which is kind of cool. And so we also have a lot of amorphous solids, and a lot of materials are just amorphous, and that just means they don't have a regular geometric pattern, and so no order, so basically no long-range crystal structure. And so some examples of that would be, right, your plastics or glass. So all of those are amorphous.
Or glasses.
Yeah, the glasses, it doesn't have like a crystal, like you're not growing a crystal of it. It's more distinct. All right, let's go through. So this is kind of the boring part of the chapter, but we'll start with the math. And so let's look at what this is. And so this is a heating curve. So specifically, it's of water, but you could have a heating curve of any substance. And so this is showing time on this axis, and then temperature. So it kind of got cut off over here. So temperature in Celsius and time. And sometimes you see on this axis energy. So we should have probably put energy increasing, because as we increase over time, there's also energy being added to this. And so let's look at a couple of things, because we have to look at, well, what is this diagram telling us? And so let's look at where we're starting. So notice it starts at -10 here. And so we just have our steady state change in temperature. And so notice water is a solid. And so this, we'll have to calculate how much energy goes into this based off of our heat capacity. And so what does this platform show us? What are these? Anybody know? Yeah, our phase change. And so anytime we have a plateau, this is our phase change. And so of course, right, we can analyze our diagram. Well, this was solid, it's going to liquid. So this is our melting phase. And right, we're melting in the forward direction, or we could have crystallizing or freezing in the reverse direction, right? So if we're taking away energy, we would be going from a liquid to a solid. So either way, that's what that state, that platform is telling us, a state change. And so again, right, time is increasing. And so now we're still at 0, except now it's a liquid. And so now we can start to increase the temperature. So again, this is related to heat capacity of our water. So we'll look into the math. And now we're at 100. So what's the significance of 100 degrees here? boiling, right? So that's our boiling point. So that matches up. We have our plateau again. So we're going to have another state change. And so, of course, now we're going, so we're boiling. If we're going in the forward direction, we could be condensing back down in the reverse. And so just appreciate right now, again, we'll put some numbers and go through the math in a second. Appreciate how large that value is, right? So probably a lot of energy that has to go into that state change. And so notice now we're at the gas phase. And so, of course, then we can just continue to increase our temperature of our gas from here. All right, so let's go through this in more detail. So that's just your general overview. And again, right, your tips are, well, we have our boiling point, and that should correspond to our state change. And then for water, right, we know our freezing point, and again, that corresponds to a state change. So we could do it, again, for any substance. And so what values would we need to know? And so let's start, I'm going to skip this for now. And so let's start with our heat capacity. And you should remember this maybe from that calorimetry lab that we did at like the very end of first quarter, where we like had our calorimeter and we took into the water and the specific heat account, maybe fuzzy. Well, at least then you were just kind of given a formula. And so now we can see where that formula comes from. And so it comes from this property of heat capacity. So this would be something that we would look up. And so the important thing to note is the heat capacity is dependent on the state as well. So it gets a little tedious if you were trying to like do this on your own and look up all the values, but that's what you have to do. And so your heat capacity is also proportional, of course, to the mass. And then obviously the specific heat of the material, which again, you would have to look up. These are known quantities. And so now we can quantify how much energy we needed. And so again, it's going to be dependent on what unit your heat capacity is given in. But generally the unit, and again, just double check this, but it's generally in joules per gram and then times your degrees Celsius, or so per degree Celsius, right? So then that cancels out. So you have your mass, so mass cancels with that. And then our specific heat, which again we look up, and then times our temperature change. And this could also be in moles. Again, just be aware of that. And so let's now kind of do this overall problem. And so now this one starts off, so I have a slightly different graph here. But let's look at our overall problem, which we'll quantify. And so I want to take, I believe we're starting with 1 mole. So 1 mole of ice at negative 25 degrees Celsius. And we want to take it to steam at 125 degrees Celsius. And we want to know, well, how much energy is this? So total energy. And so now let's walk through this together, right? So I was saying let's start with our heat capacity. And so now they've kind of, I have all the math laid out for you. But again, let's walk through this together. And so we have our problem. So we said we're starting with 1 mole. And then so we have our heat capacity. Again, notice the state here. So it's saying, yes, this is for ice. And so it's a little bit lower than the heat capacity for water that you might be familiar with. Here, let me zoom in for you. And so it's 2.09 joules per gram degrees Celsius. And so now we're looking at our first segment. And so you want to take it to the state change, right? So once we get to the state change, now we have to look at other properties. And so let's do that. So that means our delta T is going to be 25, right? So we're taking it from negative 25 to 0. So we have to stop there for our state change. And so that's what's plugged in down here. So let me pull out my calculator just so we can at least do that. And so let's all make sure we have our same numbers. So 18 times our 2.09 times our 25 degrees and change. So we get 941 joules. So that's just what they got as well. All right, so we're all good with this part? Question? So in this case, it doesn't matter as much, but it's more dependent on this unit. But also remember that the Kelvin and Celsius go up by the same amount, right? So 1 degree increase in Celsius is the same as Kelvin. So yeah, it doesn't matter too much, but it is also they give it to us in those units. But yeah, since it is a difference, it's a wash. Other questions about this? All right, so now we're at the state change. And so let's go back to the part I skipped up here. And so we have these two values that we need. And so one of these is called our heat of fusion. So this is the one that we're going to need first. And so we say, so our heat of fusion is the amount required to melt 1 mole of solid, and sometimes given the enthalpy of fusion. And so again, we're going in the forward direction. So of course, this process is going to be endothermic, aka you're adding heat. And then again, right, you go reverse. It should be the exact opposite. So you have to lose that same amount of heat. And so this is just a comparison. So right, heat of fusion is for melting. And so now we can probably guess, and let's go look at it. So vaporization, once we get there, so this will be our other state change. So I'll put liquid to gas. And so we'll look up our different value for that. And what we're trying to appreciate right now is just a huge difference in energy, right? So this is our energy for melting of various substances. So they're all about just over 5 kilojoules per mole roughly. And then look at the state change for going to a gas, so you can appreciate, right, how much more energy it takes and why those particles are so far apart and moving, and all of that is in that vaporization. So water and rubbing alcohol are both around 40, and then acetone almost at 30 kilojoules per mole. And then the other thing to take away from this section is if you ever have a problem of sublimation and you can't find the value for sublimation. And so do people remember what sublimation is defined as? So what is it? Yeah, so it's either, right, a gas to a solid or solid to gas. So you're skipping that liquid phase, and so that's why it makes sense, right, that our sublimation is our fusion plus vaporization if we need that value. So again, sometimes you may find it listed, sometimes you'll just have to do the addition if you see a sublimation problem. And good examples of sublimation are either dry ice or what iodine does, where it goes back and forth. All right, so let's go back to our math problem and where we were on our curve. And so now we're at segment 2, as we're calling it. And so we said, okay, we were at 0, right? We heated it up. But now we need to do our state change. So we have to get our enthalpy of fusion. And so notice that it's given, at least in general, in different units, which you, again, just have to pay attention. And so these values are given in kilojoules per mole. And right, they would not be temperature dependent. That makes sense because we're just staying at our temperature. So it's just molar amount dependent on. And so now we can multiply it. So we said we had 1 mole of ice. And so now it's just 1 mole times our 6.02 kilojoules. Again, we would just look up this value. And so that gives us 6.02 kilojoules for that transformation there. So any questions on that leg? Okay, it's not too bad. And so now, right, we're here on the graph. So we just did our state change. And now we have to increase our temperature again. So it's dependent on our heat capacity. So let's do that. So now we're at segment 3. So just heating up our water. And so this might be the heat capacity value y'all are familiar with if you've ever seen this. And you know, generally this comes up when talking about like the ocean and why they're so good at regulating temperature. That's why we have great climate here. Part of the reason we're pretty close to the coast here. West Coast is the best coast. And yeah. And so right, we're going to take it all the way up to our boiling point. So we have to stop at 100, of course, because that's when our next state change is. And so again, we just follow our formula, mass times our specific heat times our temperature change. And so our 1 mole corresponds to 18. Our specific heat, 4.18 joules per gram degrees Celsius for water. And again, this is for water in our liquid phase. And then multiply it times 100. So let's do that. And so we get their number. So again, we can round. So 3 sig figs gives us 7,520 joules, just like they said as well. Questions about this one? Feeling okay? All right, so now we're almost to the end. The end is in sight. So another state change. So now we're here. So we're at our boiling point. So let's look at that. And so again, back to our heat of vaporization number, which we would look up for water. And so it's 40.7 kilojoules per mole. So now we can just do our math. So 1 times 40.7. So not too bad. Sorry, I don't want to go too fast either. And again, right, pay attention to your units. Just make sure that any value you're looking up on the internet is in this kilojoules per mole and not in grams or something else. All right, so now we're at the finish line, basically. So we're here. We did our state change. Our whole mole of water is now a gas. And so now let's look at that. So now we just want to take it up to 125 degrees Celsius. So note, again, a different heat capacity based upon our state. So now we're at steam. So it only has a heat capacity of 2.01 joules per gram degrees Celsius. And so let's plug this in. So we had our mass of 18 again, times our heat capacity, times our change in temperature. And so we get 904 joules again. And so now we just have to add everything up to get our total energy. So now we want to know, well, how much energy went into this whole process? And so I'll probably switch to kilojoules for my sanity's sake. And so let's go back and add it. So 0.904 kilojoules for R5 plus 40.7 plus 7.52 plus our 6.02 plus 0.941. And so we get that that took 56.1 kilojoules.
Is there a specific thing like that, like QT, for the total heat energy, or just Q is Q, or?
Yeah, you could, well, yeah, you could put it as Q. Q's fine for like energy, because yeah, it's going to be like energy added. And,
Yeah.
but you could also just say energy or. And then of course, right, again, going in reverse, it would be energy lost, or so however you want to indicate that. All right, so that's basically the math of this chapter. And so you want to be able to apply this then to any substance. So can you take kind of any heating curve and then kind of translate that, obviously given, you know, the appropriate values. And so now let's look at the theory. So we did the math, right? And we had all the numbers, but again, kind of where do those numbers come from? What are they all related to? And so now let's look at our intermolecular forces. And so as we've seen in the past, all our attractive forces are electrostatic in nature. So that can be our cation and anion, right? That's a really clear electrostatic interaction, positive, negative. But everything else is essentially still just that positive, negative interaction. And so it's just the strength of those attractions then that helps determine the state. And again, we'll see that. And we'll see how at room temperature, again, those moderate to strong forces dictate materials being solids or liquids. And so as we'll see in general, the stronger the attractive forces are, the higher the boiling point will be and the melting point. And so these forces vary in strength. So we'll look at the weakest first. And they depend on the kind of particle and then also the geometry, the shape. And of course, the stronger the attractive forces, the more the particles resist moving. And again, right, we always have particle motion. And I'll just remind ourselves of absolute zero, right, no motion. So that's our theoretical point. So we always have motion. And so again, right, the stronger the attractions, then the more energy it will take to separate them, again, leading to our higher boiling points. And this is just a reminder, right, we're not breaking the covalent bonds. Just be very clear in your language. I've heard even like CHEM students, you know, say erroneously that they're breaking covalent bonds. So you just want to make sure, right, we're talking about intermolecular forces. So why are molecules attracted to each other? So again, there has to be some sort of attractive forces between opposite charges. Could be anything, again, extreme from whole ions, or it can be our polar molecules, or even we'll look at how nonpolar molecules have these temporary charges. And then this is just our general formula. So larger charge is a stronger attraction and longer distance is a weaker attraction. Did we do that formula last quarter, like Q1, Q2 over the distance?
Yeah.
So this is kind of like related to this, right? So we can think about this, what this formula was saying, right? Saying the same thing, that our charges matter, and then of course, right, with that smaller radius, that's going to make the attraction stronger or obviously longer, a weaker attraction.
Physics flashbacks all over the place.
That's good too.
Yeah.
Everything should come together. All right, so now let's look at our weakest forces of blah, blah, blah. And so we're looking at our dispersion forces. And so they can have different names. You may have also heard van der Waal forces or London dispersion.
Are London forces and Van der Waals forces separate categories?
No, they're the
No,
same
they're the
thing.
same. Oh, okay.
Yeah, they just have different
Oh, I
names.
didn't realize they were the same.
Yeah.
They just had different names.
Yeah. So we have our van der Waal forces, or London dispersion. And so let's look at the diagram. So we have all this text, but let's look at what that text is saying. Oops. So this is a good picture here. So we have just some helium atoms. And so what we're saying is, like, let's just take a snapshot so we can just freeze them. And what if it just so happens that at this point, our 2 electrons, of course, right, they're running around the molecule, but let's just say at this one instance, they're on the left side. So we have a temporary partial negative charge. So this is, right, the sign for partial negative. And so that means our right side is going to be kind of this partial positive, since we don't have our electrons here. And then what if our neighbor is kind of doing that same thing? And it's going to have a tendency to want to kind of do that too, since again, right, we have this temporary dipole. So now, oh, if this is positive, that's also going to make it more likely to want to be this partial negative, where our electrons are on this side. And then it can kind of happen again. And of course, right, again, it's only going to be instantaneous. So they're on that side, they'll keep moving, right? Maybe they'll kind of shift over. But we do still get this attraction. And so now we can kind of look at the text and see, yes, that's what it's saying. So just those fluctuations in the electron distribution, right, from your electrons circling around. So that's enough to result in that temporary dipole. And so again, we saw how we can create temporary regions of a negative charge and a positive charge. And so that can act as an attractive force then. And so as you have a dipole in one molecule, that kind of helps induce it in the surrounding ones. And so the important thing to note is all molecules and atoms will have dispersion forces. And so that includes, right, literally everything. So just looking at water, again, since it's special. But, right, water, we'll look at its dominant force as the hydrogen bond, but it still has van der Waal forces, right? It still has electrons moving around, and that can still create more dipoles. And so this means that these van der Waal forces, or London dispersion, they are dependent on our size as well, or our molecular weight would be another way to think about it. And so we can see this trend most clearly in our noble gases. So of course, our noble gases are all nonpolar, but then we can see how they have an increasing boiling point simply because of their increasing mass, which also of course relates to their size. So helium, only 4 Kelvin versus xenon of 165 Kelvin. And so this is just more explanation. So again, we can think about our larger electron cloud, so that's more polarizable. You also just have more surface area for interaction, so that's also important. And so with surface area, that means that the shape has an effect on our dispersion forces. And so here we're looking at pentane versus neopentane. And so the first thing you want to do when we're looking at comparing is, well, how do their masses compare? And, well, they have about the same mass, and, well, they have the same formula, so that's not any factor. So they're both C5H12, right, with our neopentane. So it's just a difference in the structure. And so this is a better picture, this kind of stick model. And so you can kind of tell how they have different surface area for interaction. So our pentane can kind of stack like this. So that's nice and favorable. Versus just trying to imagine right now our neopentane. Well, that's just a smaller surface area. So they don't pack as nicely. And so we have our smaller surface area. And so again, we can see that in our boiling point. So our N-pentane, or straight chain pentane, has a boiling point of 36, so still pretty low. So pentane is still relatively low boiling, so it's a good solvent to work with. And then neopentane, so right, 9.5. So this would probably not be something that you'd want to work with in a lab. So right, 9.5, that means it's going to be a gas at room temperature, so that's not too useful. So this is also what chemists keep in mind when like trying to select your substance too, or like what solvent should I use. And so I've never dealt with neopentane because I'm sure it's a pain to work with if it's a gas, versus pentane is super common. And so we can also look at our boiling point of alkanes trends. And so this helps us show the molecular weight difference. And so obviously increasing molar mass means increasing boiling point. So we have octane, so that's in gasoline. And so there's hexane. And again, heptane and pentane are better, safer choices. You just have to keep in mind the boiling point. So it kind of depends what property you want to take advantage of. Do you want a lower boiling point pentane, or are you trying to boil something in maybe heptane? Both. I mean, I guess it depends, because the key takeaway is molecular weight. So, you know, if you need to write that down again, otherwise you can just appreciate it, take it in, right? So we're noticing just increasing molecular weight means increasing boiling point, but we're also just comparing the straight chains. And then, right, the note is important, so just any sort of branching would lower the boiling point. So we just want to make sure we take away that key point. And I should have the live notes functioning, but if they're not functioning, you can always bug me. Okay, cool. Yeah, because I know there was like a Microsoft outage this weekend or something, so I wasn't sure. And so now let's look at the next force. So now this is our next strongest force. So this is our dipole-dipole interactions. And so now this is why it's important that we can kind of determine, well, who is a polar molecule, because we see these dipole-dipole interactions are within polar molecules. And so this makes sense. So with our polar molecules, they have a permanent dipole, and right, that helps us figure out in the first place who's polar by kind of writing out our vectors and figuring out where our electron density is. And so again, our bond polarity and our geometry determine the polarity. So you guys have gotten a pretty good sense of that. And we can, though, look at the dipole moment. So we'll look at a few substances as we go through this chapter. And the dipole moment just kind of helps us quantify our polarity and helps us kind of translate our stick models to understanding what's going on. And so this is acetone here. So we can see acetone. So of course we have our carbon-oxygen bond here, and obviously oxygen is fairly electronegative. And of course, don't forget it also has lone pairs on there, which also contribute to that electron density. And so I like this electrostatic potential map with our red areas showing high electron density versus our kind of blue areas that are more kind of partial positive. And again, we have our partial positive and partial negative symbols again helping us show that. And so again, our permanent dipole, of course, adds to our attractive forces, and that raises our boiling and melting points. And so here's another comparison. And so again, you want to start off with our molar mass. So they have different formulas this time, but our molar masses are still pretty similar. So we can say, right, our London dispersion forces are the same, or at least for the most part, right, they're about the same. So same size, they're both pretty compact, so not too much effects there with their geometry. But then if we compare their boiling points or their melting points, so formaldehyde has a boiling point of -19 versus ethane of -88. And so what accounts for that difference, right? Because it's obviously not the mass. And so it has to be then from that dipole-dipole interaction. So that gives us some idea of that strength here. And this is a good chart, so let's go ahead and it says our dipole moment here. And so this is a good chart. And so I'm also just going to show you that Wikipedia also has our dipole moments. And so again, all these have pretty similar molecular weights, so all around 44-ish. All right, acetonitrile is even a little light. I'll zoom in a little bit more. And ether, right, it's got the heaviest mass, but obviously that's not the biggest influence. And so instead they're charted by their dipole moment. And so I think we've done this maybe before in this class. But usually Wikipedia has some sort of dipole moment here, so there it is in case you want to look at it or you're at home trying to compare substances. And so that's what it says on the chart, about 0.08. And so obviously, right, this is pretty nonpolar. So, right, we expect this to be nonpolar, our propane. And so notice, right, we have our ether group is kind of next with that oxygen in the middle. So it has 1.3 roughly for the dipole moment. And then slightly increasing boiling points as we continue along. So notice this ethylene oxide has this kind of weird triangle shape in the middle, so that kind of makes it more polar with the geometry. And so we have that slight increase in our dipole moment, again increasing boiling points. And so notice acetaldehyde, so now we have our oxygen kind of more on one side of our molecules, so again we're increasing polarity. And then finally acetonitrile, again super polar, so almost at our 4 for our dipole moment, and then it has our highest boiling point. So that's pretty cool. So any questions about our polarity and dipole moment? So it makes sense relatively. All right, let's take a look at our hydrogen bonding. And so hydrogen bonding is basically a special dipole-dipole interaction, and it's because it's bound to an extremely electronegative atom. And so notice it only takes place when your hydrogen is bound to either oxygen, nitrogen, or fluorine. And you can glance at your periodic table if you need to. Just remind yourself, oh yeah, they're all in the first or second row up there, right next to fluorine, right, which is extremely electronegative. And so we have to think about what happens when we have this special condition. And so again, right, star that, so it's only with nitrogen, oxygen, fluorine. And so this happens because hydrogen obviously just has one electron, and then when it's paired with these extremely electronegative elements, obviously oxygen, fluorine, and nitrogen are pulling that electron density towards them. And so then the nucleus of our proton, of our hydrogen, becomes de-shielded essentially. And so our proton is exposed, and that just means, though, that it's a very strong positive charge. And then we have, of course, our negative dipole from our oxygen. And so again, we have our electrostatic potential map, where it's really emphasizing that with our red coloring. And again, if this is, let's just say HF, we have our partial positive side there, and then partial negative on the fluorine. And so hydrogen bonding, I think it's simply wonderful. And so it's a very strong intermolecular attractive force. So it's stronger than dipole-dipole, or of course our London dispersion. And so still putting it in context, right, not as strong as our chemical bonds though. So we're saying, oh, this is so strong, but it's only 2 to 5% the strength of a covalent bond. So you don't really need to know this number, but just kind of putting it in context, right? So again, we're not breaking any bonds, we're just breaking those intermolecular forces. And so here is a good comparison of ethanol versus dimethyl ether. And so if we just glance at them without really thinking about their structure, well, they both have these oxygens in them, so right, we expect them to both be polar, but then they still have a crazy difference in our boiling point. And their molar masses are similar. So again, those dipole forces aren't the issue. And so what separates them? And so now we have to think about their structure. So our ethanol has that OH group at the end. So all alcohols, by the way, have some sort of OH group. And so that's our alcohol versus our oxygen is bonded to no hydrogens in our dimethyl ether, right? It's only bonded to carbons. So we have no hydrogen bonding versus a hydrogen bond. And so they try to help you in the structure when they wrote it here, but we can emphasize it. So no hydrogen bonding versus, and so in this one, note that ethanol only has one hydrogen bond. And so that gives it a boiling point of 78 degrees Celsius. And so this is always why I like water. So of course, right, we can throw water on there, and why it's so remarkable. Because think about its mass. So it's only 18 grams per mole. That's super, super tiny. Except, right, water has 2 hydrogen bonds. So 2 hydrogen bonds. And so that's why it has that really high boiling point of 100 degrees Celsius, right? Because that's extremely unusual. Many organics are not that high. And so that is really the power of the hydrogen bond right there. All right, let's take a little break and then we'll continue. So let's do a 5-minute-ish break. So it's maybe start up just past noon. So take a little bathroom break or whatever, stretch your legs so you don't fall asleep, and then we'll continue on with our forces.
It's not my fault, it's quick and easy and I'm out of freaking milk.
Some red wine in the back.
Not drink the wine.
For scientific purposes, I'm making it.
How old are you?
I've got 19, I've got a year and a half.
I'm sure you've never had a sip of alcohol, right?
No, I would never. No, that's illegal. It's funny how if they were to install the draft, I could be sent overseas and shot or tell somebody that I can't have a drink or.
Yeah. I know you can't buy cigs either, right?
They put it all in 21.
Yeah,
I
that's
just always, I don't get that. I'm always like, that's always one point I've always had is like, okay, if they were to install the draft, I could get sent overseas, you know? But I can't buy a drink or anything here until you're 21.
yeah.
Yeah. Brother, I don't know. Oh my goodness. I just wait to see that.
I heard about that one. Yeah.
But it looks
They're like,
Wait.
no, I don't.
You guys distracted me. It's all your fault.
But I didn't have any snacks, you know, so I was supposed to be on YouTube. Well, they put the guys in these customer mix, I just got
How'd we get here?
All right. Do we all make it back from break? Hopefully. No one fell in. All right. And so now let's look at this last attractive force, or ion dipole interaction. So this is more relevant for solutions and attractions. And so this is even more attractive, I believe, than our hydrogen bonding. But again, this is only really relevant when we're talking about things dissolving. So this is kind of explaining, well, why do ionic compounds dissolve, at least for the most part. And so now we've kind of seen this before, but again, we'll look at it again. So we have sodium chloride. So we know sodium chloride is an ionic compound, and we've seen it dissolve in water. And again, we can compare it to sugar. So now we're kind of thinking about, like, what about sugar? So sodium chloride versus sugar. And again, so why our ionic compounds dissolve so well and so rapidly is because of this ion-dipole interaction. And so this is just to emphasize, so again, our chlorine, when it dissolves in water, all those hydrogens are going to be facing our chlorine, because again, we have our hydrogen bonds, so it's really polarized already, and so that makes it really attractive, and then obviously dissolve readily. And then our cation is, of course, going to be facing our negative N from all our oxygens. And we've kind of, I feel like we've kind of touched on this, but again, this leads to kind of solubility and our solubility rules again. And then obviously, we go back to thinking about our sodium chloride. So this would be our solute interactions. And of course, that goes into the crystal lattice, right? All those attractive forces. And then versus our solvent solute interactions. So this would be solvent solute interactions. And so basically, right, are our attractive forces of the water and the salt, is that enough to disrupt, right, our crystal lattice structure? And so again, right, we can think back to solubility rules, and we'll kind of come back around to solubility later and quantify it more. And so now this is just our overview of our intermolecular forces. So again, we mainly focus on just these three, and then only think about ion dipole when we're talking about dissolving substances. And again, you can appreciate our increasing strength of our dispersion forces all the way to hydrogen bonding.
Should you go back to the chart you just said?
Right. But
Interactions, those are considered like intramolecule, like a part of this.
yeah, so are you talking about like the sodium chloride interaction? So yeah, that would be more the intramolecular forces, so quantifying that strength of their ionic bond, which we could do. And then of course, we don't account for our crystal lattice energy, but right, that obviously comes into play. Any other questions on this? All right, so now let's look at this graph. And so what do we notice about the graph? So what is this trying to show us? So it says boiling points of group 4A and 6A compounds. But what do you notice? Kind of what's an anomaly? So methane, although methane isn't too off, but yeah, water for sure is crazy. Although this is interesting for methane, why it's so low. Well, that might just be a molar mass effect. I'm not too sure. But yeah, water is, of course, our large anomaly, so it has a much higher than expected boiling point. So I kind of mentioned that earlier, again, from our 2 hydrogen bonds. And then HF is not on there, but again, keep in mind anything with a hydrogen bond is going to have an extremely high boiling point, so HF and ammonia would also be in there. And then it does mention that these are more polar, so they have a slightly higher boiling point, so we can think back to our lone pairs. So if I draw this selenium dihydride, right, selenium has 2 lone pairs, just like oxygen. Same thing with sulfur. And so now here's another chart. So this one actually shows then our anomalous water, HF, and ammonia. So again, how they violate the trend. And so meanwhile, HCl, hydrobromic, and hydroiodic kind of follow your expected trend. So kind of interesting. I find it interesting that our pH 3 is a little bit higher too, so probably some polarity effects, but yeah, they both kind of have this dip, so I'm thinking it's a molar mass thing, but not too sure. But yeah, kind of still all interesting. And so just on an exam, right, you might be expected to talk about these sorts of things. Why are they anomalies, or what do you notice? And again, you want to just remark on our general increasing boiling points with our increasing mass. So that's what we're trying to emphasize, minus those anomalies. And so now let's look at surface tension. So right, surface tension is our property of liquids that results from the tendency of liquids to minimize their surface area. Well, let's look at this fun video. I like looking at this video now. And so, right, surface tension is why things can walk on water. So I just like looking at this lizard. Oh, I muted it.
Basilisks have been nicknamed the Jesus Christ lizard. Why? This adult male, probably the father of the young lizards, can't tell us. Nor can this female, exclusive property of the territorial male. It has nothing to do with the feeding habits of the basilisk, which consists primarily of insects and berries. This predatory reptile will help reveal the secret as it stalks the young basilisk. The basilisk is called the Jesus Christ lizard because it can walk, well, really run on water. It bicycles its hind legs and...
All right, so now we're going to look at surface tension, right, which allows it to walk on water. And so, of course, what's kind of cool, well, we'll go back and look at these forces. But basically, right, what surface tension does, and why I wanted to show the lizard, is because it allows us to float things that are more dense than water. Like in the case of the lizard, right, it can walk, and of course it moves pretty quickly, so it, doesn't fall through. So it's just that quick surface tension. It moves. I mean, you guys saw how it runs really quickly and funnily, right? But it's also trying to disperse its force over a large area to take advantage, again, of that surface tension. And so now let's look at, well, what gives us surface tension? And again, we were looking at water, and so water has a pretty high surface tension. And so what is that from? And so let's just look at what this is defined as. So surface tension is the energy required to increase the surface area. And so, right, we're just comparing right now these numbers. So water has a higher surface tension than, so this is C6H6, which is benzene, which is an organic. So remember, it's this guy. So benzene. Benzene is kind of, I would put it somewhat polar-ish because of its aromatic system. And so again, what are factors affecting surface tension? So as we can imagine, so the stronger, right, our intermolecular attractive forces are, then we're going to have higher surface tension. And so raising the temperature can also reduce the surface tension. And that makes sense, right? So obviously if you have increasing energy, then that leads to increased average kinetic energy, so they're moving more, but then of course it makes it easier to stretch and break the surface. And so let's look at another demo. And so I brought with me, and so if you've never done this, you might want to play around with it later. Sorry, let me pop out my video so you can see it. And so I brought some substances. So I brought along cyclohexane. So let me draw out what cyclohexane is. Oh, my computer can't handle it. Okay, my computer sucks. I was trying to be fancy and run 2 videos, but it can't handle it. So I brought cyclohexane, which is this guy. So it does not have any double bonds. And so it's C6H12, I believe. And so each one of these has hydrogens on there. So it's a fairly nonpolar substance. I didn't want to bring hexane out, so that's how I ended up with cyclohexane. Right, but again, relatively nonpolar. And so have you guys ever done this where you take the penny and then you try to see like how many drops of water you can fit on a penny? And then so have you ever done it with an organic then as well for comparison? So that's something you want to try. Again, you can play around with this later in lab. And so I have in my unlabeled jar, super safe, water. And so let's just see how many we can get on our penny. So of course water, we said, has a pretty high surface tension. And we can see that right with how the water beads up. I kind of lost count. But how many more can I put? So right, we can see that large bubble, right? So people can see that. What if we try cyclohexane? How will it go? And so I have cyclohexane. And let's see if we can beat it up. It's actually not doing too bad. They make me a liar here. I added one of my water one just to compete with cyclohexane. Oh, is it spilled over yet?
Yeah.
Oh, there it goes. See? So you can force it to spill over. I was actually impressed with cyclohexane. Find pentanes and water, right? Oh, okay, I finally killed it. But water, right, it made a really big bubble with our surface tension. And now you can see kind of the evaporation properties as well, which is somewhat related. Right, so we can see that cyclohexane evaporating versus our water. So if you want to play around with that, feel free. I also brought ethanol, so of course ethanol has 1 hydrogen bond. So you could play around with that.
So the cyclohexane has lower surface tension.
Yep. Yep, so whichever has the lower surface tension should kind of break, and then you can play around again with other solvents. I wish I could find our pentane or heptane. And so that's a fun demo. And so viscosity is also related. So viscosity is defined as the resistance of a liquid to flow. And so they're given in these funny units of centipoise or CPs. And so for context, so water has a viscosity of 1 CP. And so again, larger in molecular attractions equal a larger viscosity. And so now this is comparing all our hydrocarbons. And so our lightest one, our pentane, so nonpolar, that has a pretty low viscosity. And then once you get up to like nonane with 9 carbons, it's almost closer to 1 there. And yeah, we'll just keep it there because I was going to say you could go crazy looking up the viscosity of other substances like honey and all those things. So obviously they would have a high viscosity. And so other factors affecting viscosity, so again, just like before, if we raise the temperature, that's going to, of course, increase, right, that molecular motion, but then that's also going to decrease our viscosity. So raising the temperature reduces the viscosity. And then this is, again, just kind of in general to help us. So the more spherical the molecular shape, the lower the viscosity. So just, again, think back to our shape and kind of our dispersion forces, right? So how well do they interact? Are they able to kind of lay flat and kind of stack like we saw with our pentanes? Or are they small like our neopentane where they have less surface contact? And so the other property that we notice is our capillary action. So capillary action is just the ability of a liquid to flow up a thin tube against the influence of gravity. And so, of course, the narrower the tube, the higher the liquid will rise. And there's 2 forces working together. So both cohesive forces. So cohesive means how well those molecules stick together. So right, basically like water, okay, that has really strong cohesive forces. We see how they bead together. And then adhesive forces are basically how much does the tube attract the liquid. And so the adhesive forces pull the surface liquid up the sides of the tube, and the cohesive forces pull at the interior liquid. And so this gives us our meniscus. And so now let's look at this. And so we're probably familiar with the meniscus of water. And so, right, we say, well, you're probably aware that the meniscus is concave for water, right, that it bends. So water kind of bends down, right, that's concave. And so now we're answering why. So it's a balance, right, of that cohesive and adhesive forces. And so it says the meniscus of our water is concave then because our water's adhesion to the glass is stronger than its cohesion to itself. So it's kind of creeping up on the sides. And then so if we compare that to mercury, so mercury is actually the opposite, kind of goes like that. And so that's called convex. So concave, convex. So you would measure, right, mercury at the meniscus. So just like water. So right, we measure at the bottom though, so mercury is a little different. And so we see that the meniscus of mercury is convex because mercury's cohesion to itself is stronger than the glass. And so this kind of goes into metallic bonding. And so metallic bonds are stronger than those intermolecular attractions. So questions about that? And so our next related property is vapor pressure. So again, we saw that vapor pressure live. Or we can think about, right, other organic substances. So again, I'll list down pentane. So pentane has a pretty low boiling point. Or your ethers, so like diethyl ether. So also has a low boiling point. Can't remember, I want to say 35. And so we had looked at that diagram. So remember we said we had our vapor pressure of water as a function versus temperature. And so again, our pressure exerted by the vapor when it's in dynamic equilibrium with its liquid is called the vapor pressure. And so all we're saying is we have, right, our pressure, so gases coming in and out. And so that's our vapor pressure. And again, the weaker the attractive forces, then the more molecules will be in vapor. And so again, that makes sense. And I often say, like, that's why when you open these, right, you're always hit with like a vapor of chemical. Like, especially if you ever open, right, the ether drum on a hot day, it's going to kind of be very vaporized and pressure and hit you in the face. Or even like ethanol or wine, I should say, or any sort of alcoholic drink, right? You smell that ethanol, but it's really just that vapor pressure that's contributing to that. So again, our weaker forces, the higher the vapor pressure, but right, remember vapor pressure just relates back to our intermolecular forces and our boiling point, so all that is related. And again, the higher the vapor pressure, the more volatile the liquid. And so again, here's just another chart kind of showing our pressure versus temperature. So right, last time we had just looked at our water and our water vapor pressure as a function of temperature. And we had mentioned, again, our normal boiling point is dictated to when our vapor pressure equals 1 atm. So that's where that line is. And then we can just see right where everything crosses. So of course, diethyl ether has a high vapor pressure corresponding to its relatively low boiling point, about 35. Same thing, right, ethanol, so it corresponds to that boiling point of 78. And so, again, we can see the small changes in temperature can make a big difference on that vapor pressure. And so now we also want to be able to interpret our phase diagrams. So our phase diagrams just help describe the different states and state changes that occur. And so we have to be able to interpret this. So our different regions represent our states. And so let's start looking at this. So here's our phase diagram for water. So sometimes they have different colors. Admittedly, this one's hard to read, in my opinion, because they have these weird symbols instead trying to help you. But you might want to highlight, right? So this is our solid area. So everything here is going to be a solid. And then check out our axes, right? So we have temperature on our x-axis here, and then pressure on kind of our y here. And note the important parts. So again, if we're looking at water for our phase diagram, we want to know our freezing point, our boiling point, and then it has our atmosphere. So right, our normal boiling point, so we can kind of highlight that. And so now let's look at other key areas. So again, solid. Now everything here is a liquid under this curve. And then everything is a gas over here. All right, so that's our basic things. And so now let's look at these different curves, and then we'll look at our triple point. And so now we can tell, so we have this line here. And so if we have a solid on one side and liquid on the other, so notice this is called our fusion, right? So going back to our heat of fusion. So this is our melting, freezing conditions. So anywhere, right, along this line, that's where melting, freezing occurs for our state change. And so now we have the same thing. So starting from here, right, so starting at the triple point, so where your gas and your liquid are right across. So this is all our vaporization curve. So they have it labeled there, right? So vaporization. So again, that's just your state change. Now from liquid to gas. All right. And so that leaves down here our sublimation curve. So this would be the conditions for sublimation anywhere along this point. All right, so that's our gas to solid. I should have switched pens. So sublimation curve here. So just identifying that. And so now let's look at other points that are key. And so this is what you'd want to do, be able to do it on an exam, you know, identify your regions, what states they are, and then kind of the lines, right? So then where's your fusion curve, your vaporization curve, sublimation curve. And so now let's look at these 2 points. So we have our critical point, so that's our furthest point on our vapor pressure curve. And so this is that supercritical fluid, so it's at this really weird liquid gas phase. I should have put a picture of it. Maybe I'll pull up a picture. And so right this point, it's just out here. So this is, again, just usually extremely extreme conditions. We often don't see the supercritical phase since it's extremely high temperatures and pressures. And then the other point we want to identify is our triple point. So it's our temperature and pressure condition in which all 3 states can exist simultaneously. And so you can see, right, that's where they all kind of meet here in the middle is that triple point. So you want to be able to identify that as well. Questions about our phase diagram? Yeah, and for supercritical, I like this picture. I think it helps kind of show what it's like. So it's showing, right, our subcritical temperatures. And so where you can see there's a difference and a boundary in our phase. And then once we get to supercritical, it's this weird, moves like a gas, dissolves things like a liquid supercritical phase. But again, it's hard to achieve, so but this gives you.
Going along that, would you get like plasma? Is that what that's going towards?
I mean, probably those. Yeah, and I mean, plasma, you know, only exists in like extreme conditions. We just don't generally talk about that, but. And so again, just more phase diagrams of being able to identify it. So now we can see, okay, I have my triple point here. So I guess kind of ask yourselves, if this was unlabeled, would you be able to kind of add some labels? And so again, right, identifying our triple point, all our curves, and we can have different substances, of course, and just being able to identify that. Let's see how far I want to go today. I guess let's talk about, I guess we can talk about this. Let's see how far we get. And so I've kind of mentioned this thing called getting our x-rays. And so at least this gives us kind of a little preview of it. And so, right, I mentioned, well, how do we figure out what a solid is, what it looks like, the structure? And so again, all that is from a X-ray structure from our crystal. And so after we've grown, a nice shaped crystal, so it doesn't have to be a square, but, it has to have some sort of shape. So we mentioned, right, a nice crystalline crystal. And generally, they can't be too thin either, so that can be an issue if they're thin. And so basically, we want them to be large enough because we're trying to hit them with X-rays. And so when we hit them with our X-rays, they strike our parallel planes of atoms and molecules in our crystal. And so basically how this works is these are pretty complex structures. So what ends up happening is usually you hire a crystallographer and he has a dedicated job, or he or she has the dedicated job of determining your structure for it, because it does get pretty complicated. But basically what happens is there's a constructive interference pattern, and the data looks crazy because it's just like all these little dots, but then they have their special computer programs as well to help them kind of figure out the identity. So that's what it spits back out. And so again, you have this constructive and destructive interference. It basically leads to your picture eventually. And again, just the key takeaway from this section is we have Bragg's law. So Bragg's law allows scientists to determine the distance between layers of atoms or molecules. And so we just have this formula where our n times our wavelength is equal to 2d sine of our angle then. So whatever our angle of incidence is. So that would be like our layers, so our N1, N2, like however many. But I don't think that we apply this too much in this class anyways. And you would need to take like a whole separate class anyways on like X-ray, crystallography, all of that gets complicated. And again, they use computer programs a lot. And so I mentioned this, that we need to grow a good crystal. And so when allowed to cool slowly, the particles in a liquid tend to arrange themselves to give maximum attractive forces. So that helps minimize the energy. And so that kind of dictates, again, what crystal pattern they form. And so that gives rise to their shape. So let me. And so this is an important vocabulary term. So our smallest unit that shows the pattern of arrangement is called our unit cell. So our unit cell is just like what's your individual molecule. And it's usually, related to the formula, but we can see that sometimes our unit cell has multiple atoms in there. But again, we'll take a closer look right now. And so let's look at our unit cells. So like I mentioned, our unit cells are three-dimensional. So they contain 2 or 3 layers of our atoms or particles. And again, the important thing is that unit cell is repeated over and over. And so each particle in the unit cell is called our lattice point. And then we have our lattice planes that are planes connecting equivalent points in a unit cell. And so this is kind of the, I'll call cheat sheet for this chapter. So this is useful, but let's go over them. And so these are the 3 main packing structures that we'll look at. So simple, cubic, body-centered, and face-centered. But we'll come back to this. So let's start with the first one. So just our simple cubic. And trying to find our example. And so with our simple cubic structure, so what we're looking at is we have a little corner of our atom on each side of these. And so again, all lengths of our edges are equal. And so this is what we need to know. So 1/8 of each corner is within the cube. So with our cubic, our simple cubic, we have 8 particles, and 1 is at each corner. So this is, I think, a good picture here. So this is our unit cells. So you can see, right, 1, 2, 3, 4, 5, 6, 7, 8. And then we can see how many total atoms we have in our unit cell. Since it's 8 corners times 1/8, so that gives us 1 atom per unit cell. And so again, I like this summary better, so that kind of helps. So there's our 1 atom, and then we have our edge length. So this is helpful in case we're trying to solve for something. And so we can see it laid out here for us, right? So we can see our radius is half of our length of our unit cell, so that's where that came from. And sorry, I'm trying to find a picture of polonium. So there aren't too many examples in real life of this simple cubic structure. So part of that is because it's not that efficient. And this is not the greatest picture, but so far, this is the one I found. And actually, this is a website that you'd want to look at. So this is the CCDC. So this is a crystal structure database collection. And so basically, every scientist, when they make their little crystal, they will upload it to this crystal structure database. And you can actually, a really good way to do research is to kind of search the database and kind of see what's been made. And it's based off of, again, their actual submitted structures, so that's nice. So this is polonium, so it's not too exciting. So this is just our elemental polonium, but again, shown here. So this is our representation, again, from an X-ray structure. And so, right, this is the associated publication that you could look at if you were interested. But again, it's shown here where we can tell, all right, there's 1 polonium on each corner. All right. Questions about our simple cubic? And again, I mentioned the packing efficiency, that this is pretty low, so it's maybe not the most efficient structure, and maybe why we don't see a lot of it in nature. All right, so now let's look at our body-centered cubic. And so maybe you can tell right away what the difference is. So we have our body-centered cubic, and so now it has 2 atoms total in the unit cell. And so let's start with our simple cubic. So just like our simple cubic, it still has 8 in those corners. So we still have 1 atom from that. And now we have an additional atom in the center. And so let's scroll down. Oh, do we not have a body-centered cubic? So we don't have a body-centered cubic slide, but we can look at the information here. So again, just comparing, except the edge length. So if we needed our edge length in terms of our R, so it would be 4 times our radius over the square root of 3. So that relates to our radius of our atom there. And so let me pull up some pictures. Oh my gosh, that was a bad picture. So, that is a, oh, where's a good picture? Sorry, just trying to find a decent picture of iron. That's kind of shitty. I don't know why this one isn't better. That's irritating. Let's see if we can find chromium. None of these really are showing a good picture for some reason. A little frustrating. Well, I'll try to find better pictures, so I'll write down some examples. I don't know why the internet is failing. So iron and chromium and niobium, are all natural examples of these body-centered cubics. But that's irritating. All right, let's look at our face-centered cubic then. And so now our face-centered cubic, so now we have a lot of particles in here. And so we still have our 8 atoms on our corners. So 1/8 of each corner particle. So now that gives us 1 from our corners. And then it says half of each face of the particle lies in our unit cell. So we have, right, 6 faces. So our top face, our bottom face, and then our 4 sides, right? So we have 4 sides on our cube, and each one of those sides has half a face. So we have our 6 atoms in our face. So do we all see that, how we have half of a 6? And so then our math is 6 times a half, and so that gives us 3 atoms. So 3 plus 1 gives us 4 particles in our unit cell. So that matches with our cheat sheet here. So our 4 atoms in a unit cell. And so this one, there tends to be more face-centered cubic examples since it does have now a higher packing efficiency. So we kind of notice that as we've increased. So now face-centered is the most efficient at 74%. And so this is supposed to be our face-centered. So it's kind of hard to tell, but maybe you can see it from this structure. So right, we have our 8 on our corners. So 1, 2, 3, 4, 5, 6, 7, 8. And then all the other ones, they look kind of weird because they're just kind of floating. But we have our face ones, so our top face, our bottom face, and then our sides, so 1, 2, 3, 4. So that's where all the atoms are. So we can see that, and then of course we can see that other metals also pack in this way. So copper and nickel and platinum. Any questions about this?
Is it possible to get 100% efficiency?
I would have to, I doubt there's 100% efficiency, but, so let's see, what crystal? Now we have to try to ask the literature. Oh, and so another good example, by the way, of face-centered cubic, I forgot to mention, is sodium chloride is actually face-centered cubic. internet will overload. All right, I'll try to see if the internet loads. And then, so our lab today, I'll talk briefly about our lab. So it's our distillation lab, so that should be pretty fun. So we'll be trying to distill off some Franzia and separate it into its ethanol and water mixtures. And then we'll do a flame test, so just be cautious and wary of that, so make sure you hair tied up and all that good stuff. Anything else we need to talk about? All right, so I will see you in lab then in 30 minutes or so.
Yes.